Hi, I'm Dr. Mike Ducey with the Department of Chemistry at Missouri Western State University, and I'm going to be presenting on a project that we've been working on in our chemical instrumentation course that allows students to migrate through the course with a thematic approach. So let me go ahead. I'm going to jump into my presentation here and tell you about it. So before I begin, I wanted to make sure I extend my thanks to the Center for Teaching and Learning at Missouri Western State University for putting together this virtual scholarship summit. It's really a wonderful opportunity for those of us at Missouri Western to be able to present in the age of COVID and actually have a little bit of flexibility in maybe some of the things that we talk about and the formats that we use. So like I said, I'm going to tell you about a natural products themed sequence of experiments that I put together for use in our chemical instrumentation course. I'm going to kind of give you some background to this, sort of set the stage for what the students are doing this semester. And I would say, as I get started, this is a work in progress. I had hoped to be able to run through this, this sequence of experiments last spring with our instrumental methods course, the Chem 426 course. Of course, COVID got in the way of that, and we only got a few experiments in before we ended up having to leave campus. And so I was excited for the Chem 326 course to come around on my schedule and be able to engage the students in instrumental analysis in this sequence of courses. So I'll give you a little bit of introduction here and sort of the why and the how this fits into our curriculum. In the Department of Chemistry, we have set a goal that 100% of our students that are going through chemistry department programs participate in a substantive applied learning experience. Chem 326 is a really good opportunity to help meet that goal because it is taken by such a broad section of our programs. Students in the BS chemistry program, the ACS certified option of the biochemistry and molecular biology program, the medical lab science program, and then those that choose it as an elective option in the BS BMB program and the chemistry minor would all be able to engage in this kind of experience. And so this hits the vast majority of the programs associated with the Department of Chemistry. This is also kind of serves as a part of our layered applied learning approach that we have in the Department of Chemistry. In our programs, students come in their very first course in chemistry, they're engaging in an applied learning experience, and then we try and build on that each year to engage them in deeper and more meaningful applied learning experiences. And so this is essentially one of those culminating experiences within the curriculum as it relates to applied learning. It is certainly the culminating experience for students in our instrumentation across the curriculum approach. So in order to make sure that our students, our graduates, that is, are prepared to go out into the workforce, we use an instrumentation across the curriculum process where students are exposed and trained in different aspects of instrumentation in every course that they take within the chemistry curriculum. And then this course brings all of those pieces together for this culminating experience. The really exciting parts of this is this idea of having a thematic approach is that provides context and connectivity to this huge broad array of techniques that we cover in the course. And I'm going to show you an example of all of the topics that we have to cover in this particular course. And then, of course, very importantly, it provides experience that's relative to future employment. So we don't want students to simply get an exposure to chemical instrumentation. We want them to be able to use chemical instrumentation when they get out into the workforce. As I noted, there are a lot of topics associated with this particular course, all of chemical instrumentation nearly all that we have available at Missouri Western we address in this course. In the classroom, of course, we're talking about the fundamental aspects of it, the theory associated with it, certainly the experimental aspects of it, but in the laboratory is the student's opportunity to get in and use this stuff. So one of the things that is challenging is to keep this from simply being okay, here's a technique, and then here's another technique, and then here's another technique. So how do we tie all the pieces together? And so that's really what I'm trying to do with this approach using natural products, and I'm going to use that very broadly. So forgive me if I might not be using your exact definition or understanding of natural products, but really talking about this natural products theme as the connecting theme between all of the pieces. Now, what you see here in blue are the techniques that we have brought into the laboratory as part of this thematic approach. So everything in blue, the students engaged in an experiment that had a natural products or agricultural or consumer product kind of theme associated with it. And so I'm going to go through and just touch on each of these experiments so you kind of get a sense of what it is that we were doing. Sorry, I'm going to make sure that I don't go, oops, I guess I didn't start my timer. So, I'll do the best I can here. I was going to try and make sure that I stayed on time, so I will continue on here. So the experimental sequence that we used looks like this. So in total, the students do about 10 different experiments over the course of the semester, and then at the end of the term they engage in a capstone experience. Now, if you're doing the math, there's not 10 up here, and that's because at the front end of this course we have some experiments that aren't part of the thematic piece that introduce students to some of the very fundamental aspects of instrumentation. You can see the natural products piece associated with each of these. So looking at structural characterization of curcumin, which is found in turmeric, quantitation of alpha and beta humulones in brewing hops, and so on. So we really had a really nice array of experiments that kept the students' attention, provided some meaning and context to the experiments that they were engaging in. So what I'd like to do is talk to you briefly about each of the experiments and what our focus was associated with that, what the primary instrumentation focus was, and then how we were able to pull some peripheral components associated with what the students were learning into that as well. So I'm going to start with the humulones in brewing hops. So this is really one of the very first experiments that the students engaged in toward the beginning of the semester that allowed them to connect natural products to chemical instrumentation. So the focus of this particular experiment was on ultraviolet visible spectrophotometer and the use of that particular piece of instrumentation. Now, I will say that the students actually get a lot of exposure to UV vis spectrophotometry over the 4 years that they spend in program. And so what I didn't want to do was have this just be another one of those exposures. So this is a more complicated experiment that they get exposed to because they have to quantify alpha humulones, beta humulones, and then there is also a third component that is found in brewing hops as well that is related to the humulone family. So really 3 components that are in this mixture that they have to identify and quantify. So there were some additional skills that they're exposed to. One is sample preparation, and that actually we give them a lot of exposure to sample preparation of different forms, but it was that multi-component analysis that they really had to engage in. In this particular case, because if you look at the family of alpha humulones and the beta humulones, they are very similar in structure. And so they do have differences in their absorption characteristics. And so we have what would be referred to as well-resolved spectra. So the students had to do 2-component analysis, and then they also had to learn how to do a 3-component analysis. This was really new to them because the 2-component analysis, for example, we have them solve using a matrix approach, and the 3-component analysis they do through an iterative approach. And so this is kind of a fun experiment because they're doing something that they've heard of. Of course, if they happen to maybe drink beer, then they really understand this idea of hops and what it does to the taste of that brew. But what I did in the process here, I gave them 2 different samples. One was a glacier hops, which is a low amount of alpha humulones, and then a magnum hops, which is a high amount of alpha humulones. And then they had to do the extraction of those humulones and the characterization. This is also a really nice experiment because if they do it correctly, then they get very good results, very close to the reported values on the packages. Now, at this point, I also have to say I didn't create all of the experiments that you will see. Some of these I did, but many of these were adapted by experiments already found in the literature. And so what I'm doing here in part is just collecting them up as part of this sequence. One of the next things that we did, so the first half of this course is really focused on molecular spectroscopy. And so the next piece that we did was to look at emission spectroscopy. So they were looking at fluorescence in this particular case. And so we were using a fluorescence spectrophotometer. So that was the instrumental focus. And then the side focus was that they were practicing standard calibration methods. So that's another piece that you're going to see as we go through this, was the students really need to be sure that they're getting exposed to a variety of calibration methods, because out in the workforce, they'll encounter all of these. So we want them to have some familiarity with all of the calibration methods. So in the experiment, the students had to identify excitation maxima and emission maxima in order to identify the operating conditions associated with the instrumental analysis, generating their calibration curves. And then what we had them do was to quantify the amount of quinine found in commercial tonic waters. They really enjoyed this part. It's kind of fun because you get to see the tonic water fluoresce, and so if they'd never seen tonic water emit that beautiful blue color that it does when you expose it to UV light, it's kind of fun from that perspective. But one of the students, and I'll show you this as we get towards the end of this this discussion, took this idea and brought it into her capstone experiment as well. One of the big things that I really like students to do in the instrumentation course is to be able to pull together a number of the techniques that they learn in their organic course and have to look at all of them at the same time. And so when they're doing the structural characterization of curcumin, of course, curcumin is found in turmeric root, we used what I did was have them do the structural characterization. So knowing the structure of curcumin, assign the infrared vibrational modes, assign the proton modes in NMR, assign the carbon-13, and so on. And this is also the first time that we're bringing mass spectrometry in, so the students had to introduce their curcumin into a mass spec and look at the electron impact spectra and bring all of these pieces together to demonstrate the structure of curcumin. This is a little bit front-loaded in the course, and so what I didn't do was to say, here's curcumin, tell me what its structure was. Instead, what we did was work it from the structural perspective, tying it to the data. And so really that's one of the skill set that we're looking at, is that use of complementary data for structural determination. They really had to pull all the pieces together, and pieces that they collected the information for to address this characterization. In our atomic spectra experiment, what we had them do was to examine bioabsorption of copper 2+ cations by coffee grounds. And so the way that the experiment is constructed is the students are presented with a mock wastewater stream that contains 50 part per million of copper 2+ ions. So it could be any divalent metal ion. We were using copper in this particular case because we happened to have the hollow cathode lamp for it at the time. And so what they did was to pack a drying tube with coffee grounds, pass the mock wastewater sample through those coffee grounds, collect the effluent, and then analyze the effluent for the copper ion concentration. And that was done by atomic absorption spectroscopy. So in this approach, they find the reduction of the ion content is almost 90% when you do this. And a number of students found this intriguing, and you're going to see when we get to the capstone discussion that one of them in particular is using this approach to look at lead in another biological medium. So additional skills was to look at standard calibration methods, and then in this particular case, they're also introduced to the idea of a matrix blank. And so their blank sample, or their blank in this case, is the water passed through the coffee grounds in the absence of any lead. So they can't just use pure water because the matrix is a little bit more complicated. We really had a lot of fun when we got to the section on chromatography. And so when we were doing the gas chromatography component, what the students did was to extract terpenoids from fresh rosemary. And then to quantify those terpenoids in the rosemary extract. So sample preparation was a focus of this. And you can see the series of terpenoids that we examined in the rosemary. So these are typically found in rosemary. You'll find the rosemary extract over here. And I do want to point out, so if we look at this little guy right here, and this one right here, those were internal standards that the students used as their mechanism for calibration and quantitation. So, of course, internal standards are commonly used in chromatographic analysis, especially when you have a lot of components in your complex mixture. And so this was really one of the first times the students ever experienced a internal standard method of calibration. And and why you pick the particular internal standards that you do and what the criteria associated with it is and how you use them in the quantitative aspect of it. So they really enjoyed this one. Plus, it smells really good when you get all of these things extracted from the rosemary. Also, an extraction experiment that we did. This one was our liquid chromatography experiment. Students quantified quercetin in red wine, in particular in a Cabernet Sauvignon. We looked at quercetin concentrations because this is adapted from a Chem Ed article that describes flavonoid concentrations in a variety of red wines. You could also do these in dark berries as well. We focused on quercetin because one, it's easily separated from the other components, and two, it's the least expensive of the flavonoids for me to purchase and for the students to get, a sense of how the experiment is conducted. So they were doing liquid chromatography, and they had to isolate the quercetin from the red wine samples and then inject them into the HPLC. In this particular case, they did a standard calibration method, so they had to create their quercetin standards, inject each one, measure the response, and then plot a standard curve. But I had them do it this way because this was an opportunity for them to do calibration based on peak height as well as peak area, which are two common approaches that we employ in chromatography. What I have here is a separation of one of those wine samples, and this is the quercetin right out here, right before 10 minutes. You can see it's very clearly visible. So they got great results, very consistent results amongst all of the students in the analysis. And this also led to some capstone ideas that we'll talk about in a moment. We recently, because we're getting now towards the end of the term where I'm describing this, because this sequence of experiments is ongoing, because again, we're still wrapping out the term. Students had to create an electrode in their electrochemistry section that was sensitive to peroxide. And so the way that we do this is to use phosphomolybdate and modify a glassy carbon electrode to create a polyoxymetallate modified electrode. I love this experiment. It's one actually that I've done with students for quite a number of years. And so it's exciting because we can cover a number of the topics within electrochemical methods and wrap in the surface characterization component that we really want to expose students to as well. So they had to demonstrate cleaning of the electrode, demonstrate how they knew it was clean, create a self-assembled monolayer on the surface of the electrode so they're exposed to that concept, characterize that molecule thick layer of material that they placed on an electrode. So for many of them, this is the first time that they've even had the concept of characterizing a molecule thick layer. And then this electrode can be used to detect peroxide concentrations. Now, I have to be honest here. We because we ran out of time and we had a week where we had to cancel lab because of weather. We weren't able to do the peroxide piece of this, but I have done that peroxide piece in many years prior to this year, and it works great. So moving forward, one of the things that I would like to be able to do with this experiment is to tie it to a peroxide generating enzyme, for example, and then following the activity of that enzyme. The most recent and last programmed experiment that the students engaged in was to monitor Baker's yeast activity with a carbon dioxide selective electrode. They really had a good time with this one because they had to build that electrode. So they took a pH electrode, modified that pH electrode with a gas permeable membrane, and then had to characterize the behavior of that electrode, create a calibration curve for it, and then used it to follow the carbon dioxide production of Baker's yeast. And so you can see here the final product, for example, for that carbon dioxide selective electrode. These are student hands in there as they were constructing that. So they have a piece of tegaderm that we use as the gas permeable membrane in this experiment when they're getting ready to cover their pH electrodes. That's what we modified in order to make this work. So all that collected up together, we are now in the last few weeks of the laboratory, and this is the capstone project time. Again, I wish I could tell you how all the great things that they did during the capstone project, but we're not done with it yet. And again, I was hoping to have this with one run through last spring, but COVID is what it is. So what the students are engaging in right now is a 3-week project where they have to propose and design and carry out, and then finally to present an experiment of their own. It has to be instrument focused, and I've asked them to try and have a natural products component or an agricultural component associated with it. So what I've got here is just some of the examples. There's actually 16 students in this course this year, so I don't have all of their projects listed, but you can see the wide variety of things that they chose to do. I certainly did not dissuade them from taking examples from the experiments that we did during the term and then modifying those to look at a different chemical question or even a related chemical question. So we've got some really great ones that they're going to be starting on Tuesday of this week, including looking at quinine concentration in cinchona bark tea. So this is a bark that if you brew it, you extract quinine from that. Looking at flavonoid concentrations, in particular quercetin concentration in red wine as a function of growing region. Looking at terpenoid profiles in orange varietals. I have a group that is looking at phosphate runoff into regional ponds and streams, and this group is taking a little bit of a geographic approach to the project. So everybody's looking at different ponds and streams with different runoff conditions, looking at lead uptake in radish root and so on. So one of the really fun ones that I'm very interested in seeing the results of is looking at lead bioabsorption in brown and green algae. So there's a saltwater algae and a freshwater algae that we're going to see how they do in terms of lead bioabsorption. So unfortunately, I don't know how long I've talked for, so hopefully it's around 20 minutes. I guess we'll find out when I shut off Panopto and find out. But what we're going to be doing in the future is to continue this approach. And I've learned a few things along the way at this point. I'm sure we'll learn a few more as the capstone part finishes up. I would definitely like to add a flipped laboratory component to this where the students are getting a little bit more instruction through recorded videos and demonstrations prior to them coming into the lab, so we can really focus on the instrumentation, use of the instrumentation, and the experiment itself when they get into lab. So we only have 3 hours in a week to do this, and so we really have to maximize that time. And then exploring, and hopefully you see this part of it, that you could easily insert a research question as a central thematic component as well, and be able to take students all the way through different aspects of a research question from an instrumental perspective. And I think that that would be really fun, and could, quite frankly, for that group of students, could result in publications at the end of that term, and certainly possible presentations in regional and national meetings related to that central research question. All right, so I'm going to go ahead and wrap up. I definitely have to say big thanks to the students in my Chem 426 Instrumental Methods course last spring, and the students in Chem 326 Instrumental Analysis this spring, for all the great work that they do, their patience as we go through these, because it is applied learning, and so I don't always know the answers to the questions that we're posing, and so in many ways we've been learning together as we've gone through this. And finally, I'd say thank you for your time in watching this presentation. And certainly, if you have any questions, please reach out to me. I'd be happy to answer them.